Good afternoon to everybody and welcome to this webinar by 3D Seram, Multimaterial Ceramics and 3D Printing for Electronics. I will be your host for the next hour. My name is Vincent Auclair. I work for 3D Seram. I'm after sales manager and sales representative for the company. We will be talking about multi-material 3D printing for the next hour. Myself, to start with, to introduce the company and the technology. And then I will share the stage with Mr. Vincent Pateloup, who is assistant professor at the Ceramic Research Institute in Limoges, who will talk about more concrete cases on multi-material 3D printing. To start with, just a slide on a few rules and what we will do. So before we start, your microphone has been switched off, so don't worry if you can't turn it on. It's normal. It won't be switched on. If you've got any questions, just feel free to ask them in the chat. We will have a Q&A session at the end of the presentation. The idea is that we leave 15 to 20 minutes at the end so that we can answer every question. Just as another reminder, this session has been recorded and you will all have the recording link following this webinar, probably by the end of the week or in the next few days. So just a few slides to introduce 3D Seram to the people of you that are here and that don't know us. So 3D Seram is a company based in Limoges, so a French company, who define themselves as a process provider. So we provide the machines, mainly SLA machine, through a full range of machine, the cleaning device, the kiln to process the parts. We also make our own software, so the printing software, the preparation software, also tools to analyze data during production. We also supply the mix, all the raw material for the printers when it comes to oxide, non-oxide, and development slurries. And we also provide services like maintenance, support, and training to accompany customers on their way to 3D printing. So the process of 3D printing technical ceramics by SLA is quite straightforward. So you start from a CAD file, you then prepare a tank. That's what you see on the second picture. You then go on to 3D printing on here by SLA. So we do a small layer that we cure. Then we recycle all the slurry that hasn't been polymerized. We then go on to debinding, sintering, to obtain the functional part and final part with the correct dimension and density. The range of machine in SLA at 3D Seram is composed by 4 machines, from the C101, which has got a 100 by 100 by 150 millimeter platform that incorporates one laser. It comes in 3 different types. The lab version, that's made more for development. The fab version, that's more designed for industrial, so that they can scale up to the bigger machines. And the hybrid version that we will detail a bit more later on. We also got the C900 Flex machine, or hybrids. That's the historical machine for 3D Seram. That's the first machine that we worked on. Build platform of 300 by 300 on a 100 millimeter Z-axis with one laser. And then the bigger machines, we've got the C1000 Flexmatic that we come out with last year, 320 by 320 on a 200 millimeter Z-axis, incorporating 2 lasers. And the bigger machine on the market, the C3600 Ultimate with a 600 by 600 millimeter platform over a 300 millimeter course for the Z-axis. And that machine is working with 4 lasers. So the advantage of the technology of the SLA is that you can use free link support because of the way that we are building parts. We go bottom to top. So the support don't need link between the, we don't need links between the support and the part, because the parts are sitting directly on their support through the fabrication and then through debinding and sintering if they were support for sintering. With SLA, you end up with an high quality surface, roughness of around 1 to 2 microns for alumina and zirconia. We got slurry with a high loading content, around about 50 to 60%, and so a low shrinkage during firing. Just as an example, you do get 18% for alumina, 21% for zirconia. On to multi-material printing now. So the hybrid system is an option that can be put on 2 of our machines at present. The C900 that you see on the top and the C101 that you see at the bottom. They both work with different systems. So the idea is to have the SLA base material, so alumina, zirconia, aluminum nitride, whatever SLA material that you would like to use. And then you can have an additional material, 1 to 3, depending on the machine and the application, that we are dispensing through a dispersing system. So 1 material for the C101, up to 3 material on the C900. There is several dispensing systems that are available. Micro dispensing, for example, is one of them. Next, inkjet printing's been done. Robocasting can also be done, or a customized solution. At the minute, you can print ceramic with ceramic, ceramic with metal, ceramic with polymer. Whatever association that you would like to make is feasible, depending on the type of dispensing system that you would use. So very important to emphasize that the choice of dispensing equipment is open. It very much depends on the material that you want to dispense. So its resistance to temperature, the rheology of the material, the precision that you want to achieve. At the minute, we are using micro dispensing on the C101, for example, but we are open to work on other technologies if you wanted to do something else than what we are doing. The idea is to provide you with the toolbox so that you can work to what you want to work to. Just a little bit of an insight on the C101 hybrid. So just to show you how it works on the machine, little process flow chart. So it's the same principle as normal SLA. So we would scrape a layer, 25 microns to 100 microns, depending on the material that we are using. We will then cure the slurry with the laser, the same as the normal process. And then we will blow away the uncured slurry. So that's the picture that you see on the right-hand side of the screen, the little plexiglass item on the left of the carriage. That's a blowing nozzle. So the idea of this is to blow away any uncured material and to create via or void where you would dispense your second material. So once you've blown away all the uncured material, you will then dispense your second material. That could be a sacrificial, that could be a sacrificial, or it could be another material like tungsten, for example. Once you've dispensed that material, you would then need to cure it or not, depending on what you want to do. In this case, if you're using sacrificial, for example, you would then need to cure it and then go back to the start of the flow chart, scrape another layer, etc., etc. Next. A few examples of what's been done. So that's been done on a C900 machine. The idea of this was to make a helicoidal design with sacrificial material, inside an alumina block. So you can see on the right-hand side of the screen, the red helicoidal, those have been made with sacrificial material. And then with a section of 0.5 millimeters, so 500 microns, that got debinded and sintered. And you can see through the light that the sacrificial has gone away. So you get the helicoidal void inside the part. This is not feasible with normal SLA because obviously cavity is closed, so you need to remove the sacrificial during the thermal process. Next. Another sacrificial application that's been done as well on the C900 that hasn't been debinded, but it's just to show you that we can see the channel that have been done on the green part. So this was a part in alumina, channels in polymer, so sacrificial. The overall part dimension are stated, sorry. And the part is composed of 22 square channels that are 3 by 3 millimeters. You can see that the channels are all well defined into the substrate, and the section views are below, just so you can see all the squares on the side, and you've got the transparent view on the right-hand side. Next. Another application, ceramic metal. Vincent will talk to you a lot more about this than I will, but just to give you a bit of example of what's been done, HTCC, LTCC. So the idea is to put a metallic layer on a ceramic substrate and embed an electronic function into a ceramic part. So for example, we use silver for LTCC, tungsten for HTCC. And we worked as well, I mean, the customer worked on new ceramic formulation as well. You can see pictures a bit everywhere of the deposition of that metal formulation. The difficulty in this being obviously the co-sintering. Yes, next. Another application, ceramic and ceramic. So you can do multi-layer parts. With the technology that I've shown you before, you can also do this with the standard 3D Seram technology, but it is an hybrid part because it's composed of 2 materials. The idea in here is to mix Si3 and 4 with alumina and to have an interface between silicon nitride and alumina in the middle. So you can see on the right-hand side on the picture on the right, you can see the printing layers. The idea is to have 100% silicon nitride at the bottom, 100% alumina at the top, and a mixture with 20% of silicon nitride in the middle to make the transition between both materials. Another example of ceramic process is the project Cell Editor with IREC. That was the first original machine that 3D Seram sold back in 2016. An hybrid printer, a C900 machine that was bought specifically for this process and this project of making SOFC stacks. The idea is to use zirconia 8Y with LSM coating on top. If you go on the next, again, there you are. So you can see the interface between the LSM and the 8Y zirconia, that the interface is well defined and that the material, the objects are fully dense. Right, thank you. That's it for me and for the slide of 3D Seram. I will introduce you to Vincent Pateloup, who's next to me. He will talk to you about development of 3D multimaterial parts by additive manufacturing. And like I said, it's an assistant professor at the Ceramic Research Institute in Limoges. So thank you again, Vincent, for being here. And I'll leave you all with him.
So hello, everybody. I'm going today to present you some works we've made in my institute in Limoges. These works have been made with 2 PhD theses and the help of Thierry Chartier, Dominique Ross, and Valérie Madrange. Next. Okay, so I'm going to present you the context of the study. After a little presentation of the 2 manufacturing processes we have used together to make an hybrid machine, and after a consequent focus on many results of parts we have been able to print before conclusion and perspectives. Next. So first, the context. As it has been presented before, we would like to develop an hybrid additive process to obtain multi-material parts, for example, ceramic or ceramic polymer or ceramic metal. In the next slide of my presentation, we will only deal with ceramics metal parts. In this way, there are two types of parts, the HTCC cofired ceramic and the low temperature cofired ceramics. For the first one, the sintering temperature is higher than 1000 degrees Celsius. The substrate is generally alumina and the metal can be tungsten or molybdenum. In the other way, LTCC parts have a sintering temperature lower than 1000 degrees Celsius, and the substrate must be alumina and glass, and then the metal can be silver, copper, or gold. What we are going to present you in the next slide is only with HTCC material. So before a little. Typical metallic network that we have made is presented in this picture. As you can see, we've got a dielectric substrate in alumina, and then many tracks that can be printed in horizontal plane or vertical, and then they are named vias. Next, please. Okay. If we look at the actual processes that are able to produce this type of HTCC parts, we have a long and fastidious process that use tape casting in order to produce many papers of alumina, and then on each slice of these alumina parts, we use screen printing in order to print metal shapes, and then slice after slice, we make a compression of the different slice to obtain a final part. This actual process has many limitations, such as, for example, a long process with many steps. We are limited in resolution. We can do ceramic layers with a thickness lower than 150 microns, and the width of the tracks must be lower than 100 micron, and the track thickness must be lower than 20 microns. Okay. In the same way, it's very difficult to obtain complex geometries such as armored vias or inclined vias, something like this. So what can be the interest of additive manufacturing? The first one is that it's a faster coupled process. We hope that we can obtain better resolution than with actual processes, and then with the use of additive manufacturing, we are sure that we can obtain more complex geometries, especially for the metal network, as presented in the pictures at the bottom of the slide, where we can print a real armored via. Okay, next. So the processes. The first, the idea is to make an hybridization of the stereolithography process with a micro extrusion process. So we have taken a 3D Seram SLR device, and we have coupled it with a robot, and this one is equipped with one or more micro extrusion heads. The first step for printing a layer is to make the substrate shape with the stereolithography process. And then after, we use the robot and the micro extrusion head to deposit one or more metal inside the slice before doing the other slide. Okay. So repeating this slice after slice, we are able to produce a multi-material part that combines ceramic and metal. Just a little focus on the stereolithography. It has been presented before. We have first to use a CAD model of the part. We have to convert it in a standard STL format. Then we slice sorry. We build it, and after we have to debend and sinter the part to obtain a finished part. As presented here, at each slice, we have to make a layer thickness of about 50 microns, and then we have to polymerize the past, sorry, to make the shape we want in the slice. Some applications are in luxury, aerospace, or biomedical. Okay. This process is used to obtain the dielectric substrate, which is made of alumina. The other process is a microextrusion process, which deals with the use of a suspension, which must be rheofluidifiant. And when we put it inside
Tank.
Sorry, inside the tank with pressure, we are able to deposit the material in the shape we want. The advantage of this process is that we have a past with a very important load of metal powder. Areas are 40%. We can make vias and tracks with a very high speed. The granulometry of the powder can be higher than 1 micrometer, and the thickness of the layer is directly linked to the nozzle diameter. Some limitation is that we have to work the past rheology for low-size nozzles, and we have to work deposit strategies in order to have good geometries at the end. This process is used to print the conductive tracks, which will be made of tungsten or molybdenum. So, results. First, we have to print 3D parts, 3D green parts, okay? Here you've got a table with the industrial target for the HTCC part and the objective we have been able to make during these 2 PhD theses. The cases which are in black are directly linked to the nozzle diameter that is used for the process deposition. On the second time, we have developed an HTCC thermal cycle, which is able to co-fire the printing and obtain some mechanical and dielectrical good characteristics. Okay, the atmosphere must be an hydrogen and argon atmosphere. Okay, we can. The first geometry we've made was to control the morphology of the tracks. As you can see on these pictures, we have deposited one track of tungsten, which has a thickness of 150 micrometer on the top size of an alumina substrate. You can see the dimension that we are able to have. We have controlled the continuity of the track. And if we use tungsten, we obtain a conductivity of about 1.3 10 power 6. And if you use molybdenum, sorry, we can obtain a conductivity of 5.3 10.6. It's of the bulk conductivity divided by 5, approximately. Okay, so it's good, it runs, and then we try to make tracks that are inside the substrate, the aluminum substrate. As you can see here, you've got the thickness of the tracks that are of about 35 micrometers, and the higher of the tracks, which is about 36 micrometers. There is a good continuity of material between the alumina and the metal, and the tracks are totally conductive from one side of the part to the other side. Here you can see another type of geometry with a vertical via in order to connect the inside tracks of the HTCC part with another component, for example. We can see that we are able to fill vias. All the vias are connected with the tracks, and we've got a similar conductivity. Another geometry is armored vias. As you can see on the picture in the bottom of the slide, we have printed at the center a via, which is connected to an horizontal tracks. And then we have made a cylinder of metal of about 5 mm diameters in order to armor the via. Here we can see that this type of geometry has been able to be made with the use of additive manufacturing technologies, and this geometry is not feasible by conventional methods. The armored via has been well filled and is okay for us on its shape. Here you can see a multi-layer part with 3 tungsten tracks between alumina substrate of about 450 and 20 microns. We can see 3 layers with constant track thickness and conductivity between each layers using vertical vias. Here we try to make inclined vias with 20-degree tilt. The whole preparation has been made with a drilling tool, and then the via has been filled. And we can say at the end, after head treatment, that we've got a good conductivity between tracks and vias. As we have tested many complex shapes, we have decided to make real HTCC parts for microelectronics use. And here we have made a microstrip resonator that has been designed by our colleagues at the XLIM Institute. Okay, at the left of the picture, you can see the original geometry that has been simulated and designed to obtain a good component. And then at the right of the picture, you can see the design part we have changed in order to have a better conductivity of the metal. And as you can see, all the vertical vias, which are in blue on the left, have been replaced by a vertical wall in red, which is very more conductive for the component. At the bottom of the slide, you can see the printing strategy that has been developed. First, we begin with the manufacturing plate. After, we print the total alumina substrate. Then we clean the top of the substrate in order to print the metal plane. After, we print the metal walls that replace the original vias. And then at the top of the part, we print the metal surface geometry. Here, you have some pictures that see what has been able to be printed. Okay, for the first microstrip technology. As you can see, we have got a difference that is presented in the table between the design part and the printed one, and especially for the gap between lines and mass geometry. And the gap between lines, it has been explained by many problems we've got, and particularly with the accuracy of the used robot, which is not able to make metal shapes with nozzle lower than 150 micron. So to answer to this problem, we have decided to change the robot on the machine and use the same type of device as it has been presented by 3D Seram in his devices. Okay. On the right of the slide, you can see the frequency answer of the printed component. There is a little difference between the simulated signal and the measured one. Even for the S11 signal and the S21 signal, but in each case, we can see the two resonance peaks that appears not exactly at the same frequency that in the simulation, but this can be explained by the difference of printed geometries. Another one part that has been presented here is in the same type. Okay, you can see the metal shape that has been able to be printed, the difference between the design and the printed part, and in the right graph, you can see the real answer of the component, and with the three black vertical lines, the theoretical simulated resonant peaks. As you can see, there is a little offset between the simulated resonant peak and the real one, but the two one appears, and the component has a behavior that could be predicted by the simulation. Okay. So to conclude, we can see that an hybrid 3D printer able to make ceramic and metal in the same slice, has been developed. We have developed then thermal cycles in order to sinter this part, and we can propose an integrated process for HTCC and LTCC parts. As perspective, we are now working on propose better formulations, and then the objective is to formulate a path for extrusion through 50-micron nozzle. We are working with the machine resolution in order to increase the resolution of the metallic patterns, and then we are working on the dielectric or substrate material with the use of new ceramic substrates such as aluminum nitride. Thank you for your attention, and excuse me for my English, it's not the best one.
It was fine. Thank you, Vincent, for this slide and all this work and interesting subjects. If you have any questions, don't hesitate to ask them in the chat or on the Q&A little tab if you've got any. We'll wait for your question. Just a question for me, Vincent. What is the interface between both materials? So you've got your track of tungsten, you've got your alumina part, and what is the thickness of the interface between the two?
We have made some measurements with same materials, and we can say today that the interface is lower than 2 microns thickness.
Okay, thank you. Do you guys have any questions that you would like to ask? A question from, and that's it, they're coming. Question from Mr. Shaw for you, Vincent. Does the University of Limoges have any links with the HTCC?
Our labs, the IRCER, the Ceramic Institute, Research Institute on Ceramics, has some links with the HTCC, but on this subject, we are not working together. It's only development of the institute in collaboration with 3D Seram.
Thank you, Vincent. Another question from Tang J. May I ask if the current printing time is still relatively long? And is there a way to shorten the molding time?
Concerning the SLA process, the time is the same as for a normal part. And concerning the metal deposition, it really depends of the volume of metal that is deposited in a slice. If it's only a track, we don't have to wait for the drying of the metal fast, and we can then print with times that are near classical printing times. If we make a mass plane, as I have presented the microstrip resonators, we have to wait for a too longer time for industrial application today, I think. Mm-hmm. And we are working to develop new pastes that can be dried faster, or that can be dried with an addition of laser energy or something like this.
Okay, I think that answers the question. Next question is, what about the overall shrinkage of the parts? I guess it's the same as for SLA. You will be...
Yes, concerning the substrate, it's the same as SLA of about 20%. And for the metal one, it depends on the charge of the metal passed at the beginning. And if we got some problem, but for example, sorry, for tungsten past, we have put inside the tungsten pads a little quantity of alumina in order to have a more near near one.
Yeah.
Dilatation.
Yeah. Yes. Dilatation coefficient.
Yes, something like this.
Yeah.
Okay.
Again, that answered the question. Next question is from your point of view, Vincent, what could be the possible application in the medical industry, if there is any? Do you see any? I can't think of.
Perhaps we have some ask to make some dental prosthesis. With an evolution of the elastic modulus.
Okay.
And then it needs to print with 2 materials or more.
Yeah, so
it could be, I think, a good application.
Yeah, it could be great material,
yes,
I guess, where you've got zirconia and alumina or interface between ZTA and other material. Away from the metal application that we've described, but yeah, with 2 ceramics, there would be application, I guess. Same with some people. I know that some people have been working in the past with HAP and TCP, having both material on the same imprint because one is bio-resorbable and not the other one. So the idea would be to have a core of HAP with an outside of TCP or the other way around. I'm not a specialist, but yeah, you could have 2 ceramic like this using the hybrid technology. That's... C'est pas du médical. Ah non, c'est pour les résonateurs pour le scanner. Ouais. Don't think there's any more question. If you guys haven't got any other question, we're a bit early, but I think we'll close the session. If you do have any other question that are coming to mind after the session, don't hesitate to send us an email, info@3dceram.com. We will divert your question directly to Vincent if it is directed to him, or we would answer the question directly. Like I said before, you will be able to find the recording of this webinar. We will send you a link in the next few days so that you can watch it again when you want to. Thank you for your attention, and I wish you all a pleasant afternoon, and I'll see you all very soon. Bye.